In this video, I'd like to talk about SN2 reactions. And this is one of the two key mechanisms that I introduced in the primer video. And SN2 stands for nucleophilic substitution bimolecular. And of course, as I mentioned in the primer video, what that means is that the rate determining step of this reaction is bimolecular. It is dependent on two molecules. And the simplest way of highlighting this is by simply demonstrating a simple example. So we have a nucleophile here. Why is this nucleophilic? Because the sulfur atom has three reactive lone pairs on it, and that represents a considerable amount of electron density that can be used for nucleophilic attack. And we have a simple electrophile here. Why is this electrophilic? Well, it's because the carbon at C1 is bonded to a bromine atom, which is electron withdrawing. It's electronegative. So it's pulling electron density away from C1 and toward itself. And that leaves behind an electropositive carbon atom. And of course, the abundance of negative charge on the nucleophile simply comes in, attacks C1, and displaces the bromide. And we always draw our arrow from our source of electrons in the nucleophile. And the arrow just means we're forming a bond between the sulfur in the nucleophile and C1 on the electrophile. That's what the arrow means. And I'd just like to add something. Let's imagine our three lone pairs on the bromine in blue. And I'm going to draw the bond between bromine and C1 in red. So I hope this is clear. That's red. And our product, of course, is going to be this. And let's draw the lone pairs. So the three blue lone pairs, of course, are still blue. These are the lone pairs that bromine had before. This one, however, is red. And what I want to highlight here is that the pair of bonding electrons in the C1 bromine bond in the electrophile, this bond between C1 and bromine in the electrophile, bromine takes that pair of bonding electrons with it, and that becomes a lone pair on the bromide anion after the reaction has occurred. So the leaving group takes the pair of bonding electrons with it. And so this is generally the mechanism of any SN2 reaction. And as I mentioned, the rate determining step is bimolecular. So what does that mean? It means that the rate law here is going to be dependent on both the nucleophile and the electrophile. And that should be fairly self-evident and intuitive, I would think. In this attack here, the nucleophile is attacking the electrophile. Both of these molecules are involved in the rate determining step. And therefore, if you increase the concentration of the nucleophile, the rate will go up. If you increase the concentration of the electrophile, the rate will go up. And if you increase both, obviously, the rate will go up. So the rate of this reaction is very much dependent on both molecules in the mechanism, and that's why it's called SN2. Nucleophilic substitution bimolecular. It means that the rate determining step is bimolecular. Okay. Now, there are a couple of really important considerations in an SN2 reaction. And I would say the first one and the most important is nucleophile strength. And obviously, if you look at the rate determining step, we can see that the nucleophile is pushing the electrophile out. So that the nucleophile is coming in and sort of pushing that leaving group out. And so you can imagine a nucleophile is going to be strong depending on its ability to push. And so nucleophile strength is going to be really important here. And I don't want to get into the details of this on this particular video. I'll make a separate video on how we can identify and predict whether a nucleophile is likely to be a good nucleophile or not. I'll do that in a separate video, but I want to articulate that this is a very important consideration here, nucleophile strength. We need a strong nucleophile for SN2 because this is what's going to push the leaving group out, right? So the nucleophile has to be able to push that leaving group out. The next consideration is the leaving group strength, we can say. How good is the leaving group going to be? So we'll talk about how to judge the strength of a leaving group in a separate video. I'll make a separate video about this as well. I want to focus on these two things separately. So we won't get into it in this video, but I want to articulate that these are very, very important considerations for SN2. This is bimolecular, so the nucleophile has to be strong enough to push, and the leaving group has to be able to leave. It has to sort of be capable of pulling those electrons in the C1 leaving group bond and taking them with it, right? So the leaving group strength matters here. Okay, next is reactivity, order. And this is really the core concept for SN2 reactions. This is something that you'll need to know for your exams. It's very much something that's in all of the textbooks. And the order that you see is methyl, primary, secondary, tertiary. What this means is if the electrophile is more substituted, then the reaction becomes less reactive. And so we can explain this pretty simply by looking at let's say we use the example that I used above. Here we have a primary alkyl halide. Why primary? Because the carbon on which the bromine leaving group is substituted has one alkyl group. Okay. Here we have a secondary alkyl bromide. Why? Because there's now two alkyl groups on the electrophilic carbon. And finally, there's tertiary. Why tertiary? Because this electrophilic carbon now has three alkyl groups. And what this means is that for a nucleophile, we'll draw it down here. We'll use the same nucleophile. This nucleophile always attacks from the back in an SN2 reaction. That's a very key thing to understand. And actually, I'll explain that in a separate video as well. I don't want to get into the nuts and bolts of some of these topics. It's better left to a different video. But I will explain that in another video. It always attacks from the back and displaces the leaving group, right? In this case, in the secondary, it attacks from the back. And in this case, the tertiary, it's going to attack from the back side of the carbon leaving group bond, pushing that leaving group out. Now, the interesting thing to observe is that the more substituted that electrophilic center is, the harder it's going to be for the nucleophile to access it. And in the case of a tertiary alkyl bromide, you have these three big CH3 groups actually that are contributing to the steric crowding around this electrophilic center. And you can imagine this is kind of like a tripod almost, right? The nucleophile has to get up inside here and access this electrophilic carbon to displace the leaving group. And the more substituted it is, the harder it is for the nucleophile to get in there. And so what I'd actually like to show is if we think about a reaction coordinate diagram. Where we have energy here, and here's the reaction. So here is your starting materials. We can imagine a transition state and our products. This is going to be the primary transition state. So for primary transition state, you're looking at this attack here on the left. This one coming in and attacking the primary example, right? It's not that sterically hindered, and so the level of energy to facilitate that attack is maybe that high. Now, the one for the secondary is going to be quite a bit higher, and now we have to overcome this energy barrier. Why is the energy barrier higher for this attack? because it requires more energy for the nucleophile to access the more crowded electrophilic center in the example of the secondary. And finally, the tertiary is prohibitively high. The energy barrier for a tertiary nucleophilic attack in an SN2 reaction, it's generally too high for the chemistry to go. It's just too energetically unfavorable for the nucleophile to get into this highly sterically hindered environment around the electrophilic center and attack this carbon. So the energy barrier is just too high to overcome in this case. And this is why you basically don't see SN2 reactions happening in tertiary systems. You can see them in these, and this one, secondary, is going to be generally slow. And we can explain that slowness right here. It's got a higher energy barrier to get over in order for starting materials to go to products. And this is the reason. And this is basically something that you're going to have to memorize for your course. For an SN2 reaction, a primary goes very readily, and primary systems favor SN2 very much for this reason. The nucleophile can get in and access the backside of this carbon leaving group bond very easily. Secondary, it's a bit harder, and tertiary, it's basically not possible. It can't get in there. And so this is the reactivity order that we observe for SN2 reactions. And this is something, like I said, that you're basically going to have to memorize for your course on organic. The last thing that I want to mention is solvent. And the solvent choice is very important for SN1 and SN2. And in an SN2 reaction, we need a polar aprotic solvent. I might make a separate video on the solvent as well to sort of flesh it out more, but I want to introduce that here. So solvents like DMF, DMSO, and acetonitrile, you'll see those very often. These are polar aprotic solvents. What does that mean? It means they're polar, of course, but they don't have a proton. So a protic solvent would be like methanol. It has a proton, which is attached to an electronegative atom. And what that means is, if you were to use a polar protic solvent for an SN2 reaction, what would happen? What would happen is you would get hydrogen bonding between your delta positive hydrogens and your nucleophile. And the effect that would have would be to stabilize the nucleophile. And as I mentioned here in consideration number 2, nucleophile strength matters a lot in an SN2 reaction. It matters it's a critical consideration. And so if you choose a polar protic solvent, it will stabilize the nucleophile via hydrogen bonding and decrease the nucleophile's reactivity. And so this is why for an SN2 reaction, you want to avoid a protic solvent. And therefore that's the reason that for SN2 you need a polar aprotic solvent. So that's SN2. And in future videos, I'll probably go over some examples taken from midterms and final exams in second year organic. This is usually a really good way of highlighting some of these considerations in a practical way. And as I mentioned, I will go over how to judge a nucleophile strength and how to judge a leaving group strength in future videos. And this is where our understanding of resonance and electronegativity and some of these fundamental principles of chemistry is going to come in handy. And so we'll talk about that in a future video.